myself, Monique. Today we will be addressing current gaps in the music recommendation field, our proposed solution to fill those gaps, what we've done and where we are going with our research, and our advice to Gemstone teams. The music industry is constantly expanding and developing, allowing people access to millions of songs over the internet. This size compels the need for more efficient tools to analyze and better access this data. However, there's a large gap between highly mathematical and impersonal recommendations and the actual perceptions of users. This is due to multiple causes, including determining music similarity based solely off music theory. We want to create an efficient recommendation program that accurately represents users' musical preferences. Current companies in the music recommendation field include Pandora, Spotify, and Last.fm. Pandora uses a team of music analysts to tag songs. However, this can be very inefficient for large bodies of data and also introduces bias from the music analysts. Last.fm uses user-generated tags to determine their similarity. However, most of these tags are very ambiguous and they don't take into account the quantifiable data from the music itself. Both of these approaches lack a bridge between the mathematical model and perceptual model. Taking into account what exists currently and what gap we hope to fill, our research question is, how can music perception be incorporated into an automated recommendation program that focuses on an individual's listening preferences and listening trends? Basically, taking how listeners perceive music and meshing that with quantifiable characteristics from an audio file. In response to this question, our hypothesis is, if we can computationally analyze qualities and trends within a specific listener's song list, then we can generate a model of the user's perceptions of music in order to account for abstract factors such as mood. In other words, if we can use computers to analyze songs, then we can understand users' perceptions. The importance of our project stems from the need to generate customized recommendations to individuals in order to account for abstract factors that are not captured by numerical similarity. It is clear that people do not perceive music by the representation of numerical similarity. Therefore, we must consider abstract factors to model this perception of music. Along with that, we do not want to assume that an individual's user preference will match a general body of music preferences. We want our perception model to be tailored to the listener. And next, Abby will be discussing our present status.
So our original methodology dealt with the development of MATLAB code that would extract features from songs. And when I say features, I mean the mathematically defined concepts within music, such as key or tempo. Now, when you're extracting features from songs, you start with the song file, you translate it into its corresponding audio signal, and then you extrapolate certain data points from this signal, as we've done here in these sample graphs. The top graph is a spectrogram of the song Cups by Anna Kendrick, and it is essentially a representation of the frequency of the song over time. The bottom graph is a Mel spectrogram, which is essentially a transformation of the top graph in a different scale to represent the lower frequencies of the song. So these are only the examples of just the very baseline data that we can extract from the original audio signal. And what we were planning to do was use music theory in order to decide which higher order features we would extrapolate from this data. However, we've recently realized that this methodology is impersonal to the user's usage of this program because it fails to take into account the fact that different people can have different perceptions of the same music. So over the past month, we have been refocusing our methodology to allow the program to be more attentive to an individual's music perception. This has led our search for APIs that would generate musical features for our program that we could then incorporate in the context of music recommendation. And then we would choose certain features from this API. So the API that we ended up going with is called EchoNest. And what it essentially does is you input a song into it, and it gives you back certain values that correlate to different features within the EchoNest database. So what we're going to do in order to choose which features to use is develop a cognitive music model, which will hopefully represent the psychological effect on the individual user. In order to help us develop this music model, we have conducted 5 focus groups here on campus approved by the IRB. And what we did in these focus groups is we first asked the participants about how they went about finding new songs and what they thought about these methods for song recommendation. We then played a list of songs through 20-second excerpts and had the participants describe the music and what their overall reactions were to it. And then finally, we had an open discussion about the musical features that the participants generally focused on when they were listening to a new song. And the way we're analyzing and collecting data from these focus groups is we're highlighting certain keywords, grouping these keywords into themes, and then seeing just how frequently these themes come up throughout the focus group session. So here is our preliminary focus group data, just based off of the number of times that the recommendation method was referred to within the context of recommending new songs. So as you can see by this graph, for our participants, Pandora and Spotify were the most popular music recommendation systems that they used, followed by the participants' friends and Last.fm as somewhat popular music recommendation methods. We also gauged the participants' reactions to how these music recommendation methods were working for them. And we saw that generally the majority of users thought that Pandora and Spotify were rather unsatisfactory, and these participants expressed negative feelings towards the results they were getting from these recommendation systems. So overall, what we can generally conclude from our focus groups is that although we have these users with using these popular recommendation systems out there, there's still a need for a more efficient recommendation system. And so with that, I'm going to hand it off to Andrew, who will explain our methodology.
So, we're expediting the process of feature generation and machine learning using 2 handy tools, EchoNest and something called Valpal Wabbit, which I'll abbreviate as VW because it's a really hard name to say. EchoNest. It's a large catalog of songs and features associated with those songs, so it's our solution to the problem of feature generation. It's very easy to access. You can do so through a simple Python library, and it gives us things that range from the more easily measured, such as key, tempo, mode, to the more abstract, like valence, which is how negative or positive a song is, or perhaps energy, or speechiness, or danceability. So we have an example here of 2 queries. I know it's pretty hard to read, but I'll help you out. 2 queries for the songs Happy by Pharrell Williams and The Wilhelm Scream by James Blake. Now these are 2 songs that are very different indeed in terms of mood and energy. The score on a scale from 0 to 1 of Happy is, for valence, is a 0.97. So that's a good sanity check. Happy is a happy song. It's also got an energy of 0.7, so it's very energetic, of course. On the other end, the Wilhelm Scream has, I believe, a valence of 0.33, so pretty sad. And the energy is not much better, 0.17. So you see here how we can easily get access to these features of songs by doing simple search queries. And we could even customize those search queries to give us exactly what we are looking for when it comes to the problem of classification. Classification through machine learning, that is. So we're going to use VW, which is a handy-dandy tool for doing all sorts of lovely fast learning. We train an algorithm using one of the several optimization methods available to us through VW. And that algorithm will then classify inputs according to the first training set that we gave it, which in this case might be a user's library or some playlist that a user put in. But this is not all we can take into account. This is not all we should take into account, because we've got the cognitive music model. Now this is really the novelty of our project. We can't simply measure song similarity. We have to measure, or we have to infer rather, the qualities of a library of songs, the qualities of a person's own musical taste. So we do this by not necessarily measuring quantitative things, but taking quantitative measurements like the data we might get from EchoNest and trying to find trends or overarching motifs in the song body that were given by the user. And that way we can frame our recommendations and specify them to a given individual user. All this together, we take the input from EchoNest, the features of the songs, we train the learning algorithm, we incorporate the cognitive music model, and there we have a recommendation system. I'm going to shift gears and talk about our team composition and process for a little bit. Now, we're a pretty small team, we're 7 members large, and so we need to incorporate what I call dynamic sub-teams. Now what I mean by this is we don't have static permanent sub-teams where we have the same 3 or 2 members doing the same thing for an extended amount of time. In order to keep the distribution of work fluid and to balance our efforts, we need to be able to maybe each individual member needs to be able to go to one task and start working on that, or if there needs to be a redistribution of efforts towards something like, say, Junior Colloquia, we do that instead. It's just our way of coping with having a small team. And now we've recently instituted lab hours. It's 3 hours a week per person, and it will become much more important to actually do these lab hours as development progresses and coding becomes a very, very real thing. Now I'll pass it over to Abby so she can talk about some of the challenges we faced and some of the advice we have for freshmen.
So perhaps the biggest challenge that we faced with our original methodology was just understanding the math behind feature extraction. And as you can see here with this example of what's called a short-time Fourier transform, it's very highly mathematically complex and dense. Another challenge that we faced was just getting IRB approval for our focus groups, although that turned out to be not as difficult just because our groups involved a less than minimal risk to its participants. As far as challenges that we anticipate, really the biggest one is just being able to construct this cognitive music model based on the results from our focus groups and from the outside research that we'll be doing for music perception. As far as advice for the teams that are in their freshman and sophomore years, really the biggest thing is to ensure responsibility and accountability for everyone on the team. And this can be something as little as just making sure that you have lab hours like we now do in order to ensure that people are actually doing work and to set internal deadlines. We would like to thank our mentor, Professor Duraswamy, our librarian, Steve Henry, Dr. Skendel, and the other Gemstone staff for supporting us in our research as we progress through our refocused methodology to create this more user-centric music recommendation program.
All right, any questions? Yes, Zeke.
Hi. So when you were analyzing, I wrote it down because it was at the beginning of the presentation, but when you were analyzing positive and negative expressions of like the websites and the computing software that people use, did you take into account like the 5-to-1 cognitive weight of negative events as opposed to positive ones?
So the question was, when we were analyzing the various expressions of the members of our focus group on how they felt about the various websites and recommending systems, did we take into account the 5-to-1 weight on negative responses versus positive responses?
Like people remember negative events 5 times more than they'll remember positive events or experiences.
Okay. So the big thing is that this is just our preliminary data. We just conducted these focus groups about a month ago. So we haven't gone through and done all of the analysis that we're going to do. So far it's just straight out positive, negative data. You do bring up a very good point though with that, and that is something that we have noted that we're going to be taking into account once we do a more complex analysis of our focus group data.
So I guess based on your focus group, you guys are looking at extrapolate some of the negative things and fix your program. Do you have any plans to, or how do you plan on gauging the effectiveness of it? To say, you guys can have on data collections by analyzing songs, but do you have any plans to actually implement or perhaps recruit the same focus group individuals to maybe see if there's an improvement to know if your product actually, or your program is effective or not?
So essentially how to garner feedback on our actual end goal product, our solution.
So one important part is we're taking the features and we're playing those tracks for the individuals in the focus groups. And we're trying to get data from them about what they're latching on to, so what sort of features. There's lots of talk about tempo or even danceability is coming up. So we're trying to see what the individuals are noting in music. And that's what we're going to take into account when we grab these features from EchoNest. We're going to try to get that as our initial weighting system about what features are important. And then eventually we do hope to try to do some surveys, not necessarily with the same focus group members, but gauging whether or not the recommendations we make are satisfactory for the individuals.
In the back there?
So machine learning is kind of a vague term, and you describe like these optimizations. Could you go into detail about maybe the optimizations you could have chosen, which one you chose, and why? Like, why were you better than the other ones? by any chance?
So the question is, or the request is for us to go into detail about the optimizations, the specific optimizations that we choose for our machine learning process. This is kind of a hard question to answer at this moment because we've just recently come kind of into knowledge as far as this Valpal Wabbit software goes. It was actually recommended to us by our mentor very recently. And we're still actually going to receive training on it soon. So we don't necessarily have an understanding of which optimization method we're going to choose thus far, but that should be further research down the line, and very, very soon.
An easy answer, although it doesn't provide as accurate a description as we'd like to, because as was mentioned, we're not able to at this point, given the new tool, is given weighted parameters about the different features. As was mentioned during the presentation, different features are more apparent to different listeners. So having a program that can self-adjust the weight of these features in the recommendation process will be a big component for making a user-centric recommendation method. So.
You mentioned that you were going to play 20-second clips of music. How are you going to account for certain songs being incredibly dynamic throughout, especially like 7-minute long songs?
Well, like, the question was how, in playing the 20 seconds of sample music that we did during our focus groups, how did we account for a song that is perhaps maybe very repetitious versus a song that is very dynamic? Is that the question?
Yeah.
So the easy answer, again, is we're not. Given a 20-second song excerpt, the amount of variability, the amount of dynamic expression that can be done in the 20 seconds is very, very minimal, unless it's an extremely dynamic song. However, because of the limit of the scope of the 20-second excerpt, we are able to, it is more apparent which features the listener zooms in on. It makes them, in a way, more sensitive to things that they might not have commented on otherwise. It sort of zooms in on the song to a specific section. So, this wasn't originally an intended effect, we just did it for the sake of time. We realized after we started discussing preliminary results that although we did not get a scope, we did not get a sense of progression through the song, of course, what we did get is a very visible impact. Just a brief example is one of the songs had a certain effect that annoyed a lot of the listeners, and that was commented on immediately. So things like that bring, in this case, to light the importance of certain timbres to the users listening.
We have time for one more question. Right there.
When you guys kind of got onto what you were talking about with the listening first, did you play from like different genres or the same genre, or how did you decide what kind of song?
Okay.
So how did we decide what kinds of songs to play?
Okay, we actually tried to choose from a great variety of genres. Obviously, you can't cover every single genre since we only had 8 clips, but we tried to pull things from folk music, pop music, different styles of rock, jazz, hip-hop, so that we could, because people do have different tastes for different genres, so that we hoped that by having a large variety of genres, that we would be able to counteract some of the biases that might come in from people just preferring one or the other.
Thank you very much.